Okay. All right. So thus far, what we've done is we've looked at different aspects of thermochemistry. We looked at energy in general. When you take a physics course, you will have more kind of details and technical aspects of what energy is. We've looked at internal energy and how that relates to work and heat, right? So there's two ways that a chemical reaction can exchange energy with the environment, and that's through work, through mechanical work, which would be compressing a gas or expanding a gas. And the second one is through heat, through temperature differences. So heat can flow from one region to another. And what we'll do is we'll talk a little bit more about heat when we get into chapter 10, which is gases. We'll talk a little bit about the molecular level of what heat is, okay? So then we looked at a practical aspect of measuring heat, which is called enthalpy or enthalpy change, delta H. And that chemists typically, the way we classify a reaction in terms of its energy is through enthalpy change or heats of reactions. So each reaction produces or releases a certain amount of heat or absorbs a certain amount of heat. We looked at how we measured heat through calorimetry. We used that calorimetry equation, Q equals mc delta T, so that we could calculate it. And now what we're going to do is we're going to look at a specific topic, which we kind of got into yesterday, but that is the issue of standard heats of reaction. Okay, so I'm going to write the symbol for this with a little degree sign, like you were doing temperature, like degrees Celsius or degrees Fahrenheit. And then I'll put reaction there, Rx in there, okay? So we know what delta H is, right? That's a measure of heat. Rxn refers to reaction. So this is, we would call this the heat of reaction, how much energy, how much heat is associated with a particular reaction. The degrees sign, what that means is that it's being done under standard conditions. And I'll talk a little bit about that here. What do we mean by standard conditions? Okay. So yesterday, what we did was we said, hey, let's consider a reaction, a balanced reaction, a balanced equation, where we know the states of matter for the reactants and the products. And I'm going to write this number is negative 285.8 kilojoules. There we go. So when we look at this, we note that the equation is balanced, but it's written in such a way that there's 1 mole of the products, right? And that's the way we want to write these equations, is to get 1 mole of the product. And we also note that there's states of matter. So it turns out the state of matter for materials depends on the temperature, right? So like if it's really, really cold, if you're in a freezer, the standard form of ice, a standard form of water is ice. It's a solid, right? But if you're at room temperature, it's a liquid. Water is a somewhat unusual material in that you can have all 3 phases of water coexisting. So if you were to take a glass of water with ice cubes in it and then put a cap on it, actually all 3 phases of water would coexist in that. If you put in a thermos, it'll all coexist for a long time, actually. They're pretty stable. So you've got liquid, you've got solid, and then there's water vapor above the water, right? We call that humidity, right? So there'd be some humidity as well. So all 3 phases are there. But at a given temperature, there's generally a most stable form for each material. And so if you're at room temperature, the most stable form of water is liquid. If you're below the freezing point of water, the most stable form is solid. And then if you're above the boiling point, if you're above 100 degrees C, then the most stable form of water is a gas. So what this is telling us is that we have hydrogen, oxygen, and water all in some particular state, some particular phase. So typically what we do is we indicate what temperature this is happening at. So most often when you do any of these problems, it's going to be done at a given temperature, which is 25 degrees Celsius, which is also equal to 298 Kelvin. Okay. So when you look at these values, they're almost always tabulated at that specific temperature. And if you think about it, that's room temperature, right? 25 degrees C is around 78 degrees Fahrenheit. Hydrogen is a gas at that temperature, right? Like, so if you had hydrogen, it would be a gas. Oxygen, which is in the air, is clearly a gas at room temperature. Water, on the other hand, at room temperature is a liquid, right? So these states of matter are written specifically for a given temperature there, okay? So if that's the case, then what we do, so in other words, if I were to put hydrogen as a liquid, which is possible, rockets sometimes use liquid hydrogen. Rockets often use liquid oxygen, right? For those particular materials, if they're in a different state of matter, we would indicate that this is non-standard. So this at 298 Kelvin or 25, this is the standard state of all of those materials. So we put a little degree sign there. That little degree there, again, it means it's under standard conditions. So it turns out the state of matter is important because if we were to change just the water, if we were to put it into gas, for example, this is a possible reaction. We could do this. It turns out under those conditions, delta H is different. It's minus 241.8 kilojoules. So the state of matter is important. Okay. Now, what we have done is quite a bit of work over the years of tabulating different reactions. So this is called a formation reaction. And the reason it's called a formation reaction is that what you're doing is you're taking an element, right? This is an element. You're taking another element and you're making a compound. So anytime you're reacting elements to form a mole of a compound, that's called a formation reaction. So for example, here would be another one. I could take carbon. Carbon is a solid at room temperature. I could take hydrogen, which is a gas at room temperature, and I could take oxygen. Okay. And I could make a glucose molecule, which is a solid at room temperature, right? So this is glucose. All right, if you take a look at that, it's balanced and we've got 1 mole of a product. It's made from the elements, right? Everything in glucose is carbon, hydrogen, and oxygen. Those are elements. So this would be a formation reaction. Now here's one that's not a formation reaction. If I were to take this, sorry. That's not a formation reaction for a couple of reasons. One is we're not reacting elements. We're not taking carbon and hydrogen and reacting them. We're taking methane. That's a compound. Oxygen is an element. That's okay. But the methane on the left side is not an element. So that's not a formation reaction. Furthermore, there's a 2 here, right? So that's a little ambiguous. If you're getting 2 products, that's not formation either. Formation is where you make 1 mole of one product, 1 mole of a compound. So this is formation here. This is formation here, 1 mole of a product, which is a compound. Here, it's 2 products. So that wouldn't be formation either. So that's a chemical reaction. It's a balanced chemical reaction, but we wouldn't call it a formation reaction. So for that reason, when it's a formation reaction, we just want to indicate for people that it's a formation reaction. So instead of writing delta H reaction, we put F for formation. Okay, so if you see that, the F is referring to the fact that, oh, this is delta H for a reaction in which we're taking elements, reacting those elements together to get a compound. Okay, so let's take a look at an example. Oh, there we go. All right, so here's how we'll do this. I'm going to show you that equation I just wrote a moment ago. Which is not a formation, right? This is a combustion. So we're going to write, you have a choice. You could write COMB for combustion, or you could just write RXN for reaction. Okay, so some people will call this combustion, some people will call it reaction. And what we want to do is we want to figure out the value of that without having to do the experiment, without having to measure the temperature changes, without having to measure the masses and all of that. We want to find out what delta H is. Here's how we're going to do it. We're going to look at data tables for delta H of formation and use them in the following equation. So we're going to calculate it. And the equation looks like this. Delta H of combustion is equal to the sum of the number of moles of a product times delta H of formation of that product. So I'm going to put comma, that's a comma, minus the sum of the number of moles of each reactant times delta H of formation of each reactant, R for reactant, okay? Degree sign again means standard conditions, okay? So here, N sub P is the coefficient for each product. So you get that from the balanced equation. So for methane, I'm sorry, for carbon dioxide and for water, N sub P would be 1 and 2, right? You just use those coefficients, okay? N sub R is the coefficient for each reactant. So the reactants are, let me do this over here, CH4 and O2. So N sub R would be 1 and 2. Okay, so that's those numbers right there. That's these NP and NR right there. The delta H's, you look those up in a table. You just go to a table and look them up. So let me do this. I'm going to stop share here. And I'm going to see if I can find a table for you that's online. Alex has one, but I want to show you one that you can just find it on Google. Here they are. You know, it's like anything else. There's tons of them on the internet now. Okay, but there's some, you know, some that are kind of advanced and stuff. So, but let me show you here. So view image, and let me come over and share this. It's not the best quality image for you. But you'll be able to kind of see where it's coming from. Here we go. Okay. So again, it's not that great of a view of it. It's someone took a picture of it and they took a pretty low quality picture of it and they posted it online. Okay. So here you go. Notice what they have. They have the names of the materials, which is called the substance. So for example, there's glucose almost down at the bottom. Then the chemical formula with the state of matter is given next to that in the second column. And then in the third column, there's your delta H of formation, right? Delta H of formation, there's a little degree sign. You can't really see it very well. So if you look at glucose, all the way down at the bottom, that's next to the last one, it's negative 1,273, negative 1,273. And so people have tabulated thousands of materials. In fact, methane CH4 is all the way over on the right side, and it's the fourth one down from the top. It goes hydrogen chloride, hydrogen fluoride, hydrogen iodide, and then methane, CH4, negative 74.80. Okay, so you look these values up, and that's kind of cool. That's a nice aspect of this. So let me share again. Okay, all right. So let's take this equation again. Okay, and so I'm going to write down the n values. It's 1, 2, 1, 2, right? I'm just taking the coefficients and writing them down. Now I'm going to do the delta H values. Now, we just saw one of them. For methane, it was negative 74.80. So I'm just going to write negative 74.8. We don't need to be so precise that we have 2 decimal points, two digits after the decimal point. So I looked that up in the table. Then we look up oxygen. Now here's a little trick about these problems. If it's an element in its standard state, it's 0. So if you look at, remember how we talked about oxidation numbers, the oxidation number of an element is 0. Similar thing here. They're defined as 0. So O2 is an element. At 298 Kelvin or 25 degrees C, the standard state of oxygen is a gas, right? So under those conditions, an element would be 0. So you can look it up. You could look up O2, but if you see that it's an element, you can immediately say that it's 0. And that makes the calculation. Anytime you put zeros into a calculation, that makes it pretty easy, unless you're doing calculus or something. So then we look up CO2. You just look it up in the table, and carbon dioxide is negative 393.5. Okay, again, be careful. Make sure when you look it up in the table that you pay attention to the state of matter. So if you looked it up and you found CO2 solid, that's going to be a different value than CO2 gas. So just make sure you get the state of matter as well. And then liquid water is negative 285.8. Okay, these are all in the units of kilojoules or kilojoules per mole, whichever we want to put it. Either one is fine. Different authors will put different units. Okay, so now here's our goal. Our goal is to find delta H of reaction. Now this is combustion, so we can call it combustion or we can call it reaction under standard conditions. Okay, so here's how you go about it. You use that equation. So let me show you that equation again. Delta H of reaction is the sum of the number of moles of each product times delta H of formation of each product minus the sum of the number of moles of each reactant times delta H of formation of each reactant. Okay, it looks complicated, but it's actually pretty simple. All you're doing is adding numbers together and then subtracting one from the other. So let me do this part first. Sum just means add up. So it'd be like, suppose you were trying to do some kind of calculation of the average test score. And what you did was you made a little table and, 5 people got 100, and then 4 people got 90, and then 8 people got 80. What you could do is you could calculate the average of that, right? So you'd take the number that got 100. So 5 people got 100 times 100. And then you would add that to 4 people times 90, and then plus whatever, and you add all those up. That's all we're doing here. So we're taking NP for each material and multiplying it by delta H for that material, and then adding them up, the sum, okay? So keep in mind, it's products minus reactants. So don't do the reactants first, do the products first, which might be a little counterintuitive. So 1 times negative 393.5. That's the first product. So I'm just going to write 1 times minus 393.5. And then sum, so you add the second one. So the second one is the water, right? So 2 times, let me put it in parentheses, minus 285.8. Okay? And then I'm going to put this in parentheses just to kind of remind us that we're adding those together. Those are the ones we're going to add together. We're adding all the products. Sometimes I just write for myself, I just say, remind yourself, products minus reactants. Okay, and then subtract, so minus. Now you do the same thing for the reactants. Okay, so the first reactant is methane. So it's 1 times minus 74.8 plus 2 times 0. Okay, and there you go. And then you just run through that calculation and you've got your answer. So again, it's the sum, meaning you're adding up the products minus the sum, you're adding up the reactants, you're taking products minus reactants, and you just have to take the coefficient times the delta H that you look up in the table, right? And keep in mind, in the ALEX tab, these values might be slightly different. So that's just the reality of when people tabulate these things. So for example, sometimes you'll see that carbon dioxide is negative 393.49. Is that right? 49? 49, I think. So then that gives you, when you round it, negative 393.5. Sometimes people just round it to negative 394. I've seen that too. Okay. All right. So let's do the calculation. Now be careful because you've got a lot of numbers in here, right? So it's easy to get kind of messed up with it. So what I'm going to do is I'm going to do each bracket separately. So I'm going to take 393.5 negative plus 2 times 285.8 negative. Oops, I already made a mistake. 393.5 negative plus 2 times 285.8 negative. There we go. So in this first bracket, it's negative 965.1. Okay, and then we're going to subtract. This one's easier because if you look at it, 1 times negative 74.8 is just negative 74.8. And then 2 times 0 is 0. So that one's easy, negative 74.8. Combustion reactions are actually probably the easiest ones to calculate these things for because oxygen is a reactant and it's always 0. Okay. So now just be careful when you add these together. A common mistake is to get the signs wrong. So remind yourself, if you subtract a negative number, that's like adding a positive number. So this is really negative 965.1 plus 74.8. Remember, you're subtracting a negative, so that's like adding a positive. So plus 74.8, and you get negative 890.3. And just to remind you, the units are kilojoules. Okay. And there you go. So that's how you use this equation. So this is a problem where you're calculating the heat of reaction or the heat of combustion from standard enthalpies of formation, standard heats of formation, right? So these values that we looked up in the table, those are formation values. Overall, when we calculate this, this is called a reaction enthalpy change. Okay, let me show you one more example here, just to went through a lot of. Okay. All right, so here's one. So again, you're going to calculate the heat of reaction from the formation enthalpies. Okay, so here's what they give you, C2, H2. So they're giving you the balanced equation, so you don't have to balance it. Okay, now in a way, this one's a little easier because there's only 3 materials in there, right? And then again, you're going to use the ALEX data tab. Okay, so let me make a little table for you here. So I'm going to put N here, and then I'm going to put delta H of formation. Okay. So the N for here is a 1. The N for here is a 2. And the N for here is a 1. So we've got those right there. Now the delta H of formation, we get to look those up, right? But there's one of them that we know is 0, and that's this one right here. It's an element, and it's in its standard conditions, right? So at room temperature, all the problems you're doing in chemistry are at room temperature. So you can just use your intuition. Oh yeah, hydrogen is a gas, right? It's a gas at room temperature. So it's an element, it's in its standard state. So it's got to be 0. Really, you have to be an engineer to, engineers will look at if things are in their non-standard state. They have bigger tables at different temperatures, but chemists, we just need to worry about room temperature. So elements will be 0, okay? And then, so we got to look the other two up, okay? So, you know, you click on the data tab, and then you look them up. So acetylene is C2H6 is, okay, be careful with this one. It's positive 227.4. And then this last one is called ethane, which is minus 84.0. So that's from the Alex data tab. Okay, so we've got them. Again, these are all in the units of kilojoules here. So now, again, delta H of reaction, all these calculations are under standard conditions. Sum of the number of moles of each product. Oops, I don't need a comma there. Times delta H of formation of that product minus some, remember it's products minus reactants. So products minus reactants, okay? So again, I'll put brackets here so that we can do the products first. For me, I have a tendency, just my mind goes, oh, do the reactants first because it's on the left side and I'm used to going left to right. But if for this particular problem, you want to do the product side first. So 1 times negative 84. There's only one product. That's it. So we just have to add that one. Right? So that one's done. That's the product. The reactant, there's 2 of them. So 1 times positive. I'm going to put a positive in there because sometimes they're positive, sometimes they're negative. And then again, you can look up hydrogen and you'll find that it's 0. Okay. So there we go. Products minus reactants. Okay. Well, in a way, this is pretty easy, right? Because you're just going to have 1 time. So minus 84. And then minus, this is 0. So you don't have to worry about that. So minus 227.4. Okay. All right. Okay, so let's take a look at it. So we've got minus 84 minus 2. So really what you're doing is you're adding 2 negative numbers. So 84 plus 227.4, they're both negative. So you get minus 311.4. And again, the units are kilojoules. Okay. So just be careful. If you use the Alex data tab, you'll get the same values that they're calculating. If you use something out of your ebook, you'll get a slightly different value. This is also in the ebook, of course, because this is a pretty standard type of problem. But you know, for actually doing the problems on Alex, I would recommend using the data tab. It's maybe not the most convenient thing to use, but it gets you the answer that they're going to get. Okay, so these do vary a little bit depending on which table you use. So it might be 311.2 or 311.6, but they should be pretty close to each other. Okay, now I want to point out something that essentially what this is telling us is the energetics of a chemical reaction. So essentially what's happening here is, remember, everything has energy, right? Everything has that. Even space itself has energy. Empty space, a vacuum, it turns out has energy. We're not going to worry about that kind of stuff in this course, but everything in the universe has energy, even space. if you have chemicals in a container, they have energy, right? And so in a way, what we're doing is we're saying, how much energy does something have? It's the enthalpy. The enthalpy is essentially the content of energy that it has, just like internal energy does. What this is telling us is that when we do this reaction, we are releasing energy, right? In the form of heat. Now, there are ways to use fuel cells and turn it into electricity. There's ways to convert it into mechanical work so that we can move an engine. There's all kinds of things we could do with that energy. But what this is saying is that when this reaction occurs, heat is released. Heat is transferred out of the reaction. So what that means is the reaction actually has less energy after than it had before, right? If the change is negative, like a bank account, if you have less money after you pay your bills, that means that the change is negative. So here's what happens. We can think of this as being the enthalpy of the products, P for products, and the enthalpy up here of the reactants. And so here's what happened. As this chemical reaction occurs, as these atoms are reorganizing themselves, what has happened is the energy or the enthalpy has changed. Remember, a reaction goes reactant to product, right? So here's our arrow. But I'm drawing the arrow vertically because we're thinking of energy in terms of verticality, right? So what has happened is our reactants, which are C2H2 plus H2, are being converted into products, C2H6, and the energy is changing. And so what has happened is, remember when we talked about potential and kinetic energy, and we said that, you know, if you're up here, you have more potential energy, but if you ride your bike down the hill, you get more kinetic. So we have a maximum of kinetic here, and we have a maximum of potential up here. Same thing's happening here. We have chemical energy in these reactants. Think of it kind of like potential energy. There's a certain amount of energy we have the potential to use. As the reaction occurs, that energy is released in the form, whatever form, could be heat, could be electricity, could be work, but it's releasing that energy outward. And so what's happening is we're dropping down in energy from the reactant down to the product. And if we're dropping down, that means the energy is going to come out. It's got to go somewhere, right? We can't create or destroy energy. So if the reactants have more energy than the products, then when the reaction occurs, that energy's got to come out somehow. And it generally comes out as heat, as a exothermic process, right? And so there you go. So that's the significance. That's the meaning of this. This is called an energy level diagram. And we will talk more about the energy level diagram when we get to chapter 6, where we talk about the structure and the electronic structure of the atom. Okay. So there you go. So that pretty much wraps it up. I think I did actually every type of problem from chapter 5 of thermochemistry. So good luck with all of that. Let me know if you need help on it. But our next topic is now chapter 10. So we're going to skip over 6, 7, 8, 9 and go straight to 10. And then we'll come back. We'll come back to 6 after we finish 10. But we're really doing macroscopic measurements right now. So we're just talking about mass changes, volume changes, energy changes. And then we'll come back and we'll get into the nitty-gritty detail of the atoms and the molecules and do chemical bonding after we finish this. Okay. So let me put this in here. So now we're going to move on to chapter 10, which is gases. Okay. So what can we say about gases? Let's kind of start off by just talking about some general properties of gases. In general, when we consider matter, so let's make a little box here. In general, we think of there being 3 states of matter: solid, liquid, and gas, right? So here's what we know about solids. Solids generally have atoms that are really close to each other, right on top of each other. The electrons are actually in electrical contact with each other. So there are different types of solids. There's plastics and there's crystals. What I've drawn here is sort of a crystal. The crystal has atoms that are really right next to each other and they follow a regular pattern. Just like imagine that you were going to the grocery store and someone did a really good job of stacking all the oranges or all the apples to where they're in nice orderly rows, right? That's essentially our model of a crystal, and a crystal is a solid. Okay. Plastics or glasses are not quite as ordered, but the atoms are still close to each other and they're locked in rigidly. So one other aspect of solids is that in general, they don't move around with respect to each other. So if you have a piece of metal, you know, one atom in that metal doesn't move around relative to the other atoms in the metal. It's stuck. So, you know, this atom is always going to be next to these other two atoms. Now, what about a liquid? Well, a liquid is also, the atoms are pretty close to each other in a liquid, but they're more disordered, right? In general, liquids, the atoms are like maybe 10% further away from each other than solids. They're a tiny bit further away. So there's a little more spacing. Not much, but a tiny bit. The exception to that, of course, is water. Water, it turns out, the molecules of water are actually closer to each other on average in a liquid than they are in a solid. And that's unusual. That just has to do with the properties of water that make it behave that way. So one aspect of liquids that are different from solids is that these liquid molecules are able to move around, right? They have freedom. They have a degree of freedom, the ability to move with respect to each other. Okay, so that's a big difference between solids and liquids. These are both together, we refer to them as condensed matter. Meaning that those molecules or those atoms are condensed. They're really close to each other. And you can't really compress a solid or a liquid. They're incompressible, right? Solids and liquids are incompressible. Oops, I misspelled it. I don't know why I'm putting an M here. Incompressible. Which means you can't compress them. So if you squeeze on a liquid or you squeeze on a solid, it will squirt out the sides, right? It doesn't get smaller. And that's the basis for hydraulics. Hydraulics, you use liquids and you push on them and they don't compress. They actually transfer the pressure all the way through the tubes so that you can have that same pressure somewhere else. Okay. Now, what about gases? Gases are quite a bit different. And that's why we have a whole chapter on them. In gases, the molecules or the atoms are really far apart from each other. They also occupy the entire container, right? So they're spread out and they occupy the whole container. So it's often the case for gas that we will claim that the volume of the gas is equal to the volume of the container. That's different than a solid or a liquid, right? In a solid or liquid, most of the space here is empty, right? I mean, it might have air in it, but the liquid and the solid are not occupying that space there, okay? And it's often said that a gas will occupy the shape of the container, and that's true. So it's very flexible, right? Gases are very flexible. They just essentially change depending on what container you put them in there, okay? So notice there's a lot of space between the atoms. Because of that, they have a very low density relative to solids or compared with or compared to solids and liquids. So here's an example. You know, if we have copper, the density of copper is around 8.6 grams per milliliter. if you take water, liquid water, the density is about 1 gram per milliliter. And then typically gases have much lower densities, so 0.001 grams per milliliter. So very, very low densities for gases typically. Of course, the sun is a gas, but it has a very high density, but that's an unusual material. We're talking about things like air and gases that we would get out of a tank, that sort of thing. Okay, natural gas, for example. Okay, so there's a general aspect about gases. Gases are also able to diffuse. Which is interesting. So what that means is if I took some other type of gas and I introduced it, I have a little door here and I can open that door. So I introduce some gas here. It will spread out over time, right? It will diffuse through the container, and now this new gas will be mixed with the old gas, right? So they also mix very well. Okay, so that's one aspect of gases. On the other hand, if I were to suppose this was copper, chunk of copper. If I took a chunk of steel, which is also a solid, and I threw it in this container, it wouldn't mix with the copper, right? It would just fall down to the bottom and be next to the copper. It wouldn't mix very well. There's an exception to that, and that's mercury. Mercury is an interesting metal because it's a liquid. If you add solid metals to it, it actually dissolves those metals. It's highly exothermic too. So if you were to take some silver, for example, a little piece of silver and add it to some liquid mercury, the silver will actually dissolve. You'll see it dissolve just like a liquid dissolves, like a salt dissolves in water. It will dissolve into the mercury. And that's an exception to that. But generally, if they're in the solid state, they don't mix very well. Same. Okay, so there we go. All right, so there's a general kind of discussion about gases. The first thing we're really going to do with gases is we're going to talk about pressure. Okay, so let me close this here. Okay, so let's talk a little bit about pressure. Okay, so it's a kind of a long discussion. I don't want to get too much time dedicated to it, but we'll spend at least the last 10 minutes here. So pressure, let's talk about pressure. P for pressure. Pressure can be defined as the force that you're applying divided by its surface area. So I'm going to write that as F for force divided by A for area. So let me show you what I mean by that. Imagine that you have a piece of paper, and then you're going to write on that paper with a pencil. So here's your pencil. In order to write on that paper, you have to apply a force to the paper, right? You have to push down with your fingers, with your hand, onto the paper using the pencil. So there's a force being applied on that paper. In fact, you would know that's true because if you took the table away from the paper and you tried to write on it, the paper would move, right? You would accelerate the paper. So that means there's a force. In fact, that's how we define a force, acceleration of a mass. So there's a force being applied. And what we're claiming is that pressure is the force that you're applying. So you're applying a force. There's actually two forces. You'll learn that in physics, right? There's a force that the pencil is applying to the paper, but the paper is also applying a force, a counter force back to the pencil. Okay, so there's a force applied. There's also an area of contact, right? Right? There's a little area of contact right there. So that force divided by that area of contact would be the pressure. That would be the pressure that you're applying to the paper, okay? Now, suppose I did the following. Suppose I said, I'm going to do the same thing. I'm going to apply the same force. But now instead of using a pencil, I'm going to use a hypodermic needle. I'm going to use a little needle like you would use for a vaccination. These needles are amazing now. When I look at the vaccinations, just how thin these needles are. They can machine them so thin, right? Now, why do you do that? Why do you make a needle so thin? You make it thin because essentially the pressure that's applied to the skin is enormous when you put the needle in. And so it just punctures through the skin very easily because it has a very small area, right? So that paper, if we apply the same force, but now we have a smaller area, right? Instead of just pushing against the paper, it's actually going to penetrate the paper. It's actually going to go through it, right? So what we have done is we've taken a force, which is the same. We haven't changed the force, but we've divided that by a smaller area. So if this is the same, but the area is smaller, what we've done is we've made a larger pressure, right? The pressure goes up if the area gets smaller and the force is the same, okay? So that's our definition of pressure, okay? Force divided by area. Now, let me talk just real briefly. You know what? Let me talk a little bit about the units. This will come up. So this starts to come up in this chapter, chapter 10. And then it'll come up in chapters, I think chapter 6 a little bit. And then I think it's just those two chapters. So let's talk about units. There's something called the MKS system. And then there's another system called the CGS. And so unfortunately, chemists still use the CGS for some things. Physicists generally use the MKS system. So what this stands for is meters, kilograms, and seconds. So MKS. Chemists typically use centimeters, grams, and seconds. So we have to be kind of careful when we do these problems that we'll go through, because typically we want to use the MKS system. That's the one we want to use. So for example, when we do molar mass, what are the units of molar mass? Grams per mole, right? Grams, that's the CGS system, right? We want to use kilograms, but we don't typically do that when we're doing mole calculations. So that's one issue. The other issue is typically with volume, right? When we measure volumes, we measure milliliters. But what's a milliliter? A milliliter is a centimeter cubed, or a cc, right? A cubic centimeter. That's that. So we, in fact, we're using, when we do volume calculations, we're often using the CGS system instead of the MKS system. The MKS system is not really convenient for area, for volumes, because a meter cubed is so giant. A meter cubed is very large. A cc is very small, right? That's more convenient for us. But for these calculations, we want to use meters, kilograms, and seconds. Seconds is not an issue. We're always using seconds. Although in Chem 12, there are some problems where you do minutes. So it can happen too. All right. Okay, so here's the reason I want to talk about this. If we calculate what forces in the MKS system, force is equal to mass times acceleration. Okay, now I'm not going to talk much about acceleration. Acceleration is something speeding up or slowing down, okay? But we do know that mass in the MKS system has the units of kilograms, okay? And acceleration is velocity divided by time, so it's meters per second divided by seconds, or meters divided by seconds squared. Okay, so that means that the units of force that we're going to use under the MKS system is called a kilogram times a meter divided by a second squared. Now that is a little, awkward, right? It's got a lot of units in it. So typically what we do is we call it a Newton. And the abbreviation for Newton is a capital N, okay? So the Newton is N, it's really kilogram meter per second squared. Now, let's talk about pressure. P. Pressure is force over area. Area is length squared, so it'd be meters squared. So what we get here is kilogram meter per second squared, but now we got to divide it by area. So we got to divide it by meters squared, right? Area is meters squared, length squared, not acres. We're not going to use acres, okay? Or square feet. Apartments, houses are generally done in square feet. Properties are done in acres, but we're going to do meters squared for area, okay? So take a look at what happens. You've got these, now you've got a lot of units in there, right? So typically what you could do is you could cancel one of those, the meter in the numerator and one of the meters, not both, but one in the denominator, and you would get kilogram per second squared times meters. And that we're going to call a Pascal, just to give it an easier name. And the abbreviation for a Pascal is a PA. So one of the pressure units that you're going to calculate in this chapter is the Pascal. And 1 Pascal is 1 kilogram per second squared per meter. Okay, now that's still kind of awkward. So often what people will do is they'll say, look, everything that was here is a Newton, and then you're dividing it by area. So why not just do it this way? Just say Newton per meter squared. So that would also be a Pascal, right? Because the area, I'm sorry, the force is in newtons. That's a Newton right there. And then all you're doing is you're dividing it by area. You're taking that and dividing it by area. So just put meter squared in there. So just do Newton per meter squared. So you'll also see that. So you'll either see kilogram per second squared per meter, or you'll see Newton per meter squared. And that is just a common unit. Let me just save this one. It's just a common unit that's used. So let's review this. So pressure, a typical unit is the Pascal. Let me just write out pressure here. So pressure, the symbol is a P, usually a capital P. And then our units are the Pascal. And the abbreviation for the Pascal is PA. And if we really want to have it, we could say a Pascal is a kilogram per meter. I'm going to put the meter first and then the second squared. Doesn't matter which order you write them. Okay. So there's your units. Or a Newton per meter squared. Okay. Now it turns out for most of the calculations that we do in chemistry, a Pascal is such a small amount of pressure that we end up with large numbers of Pascal. So like the pressure of the atmosphere, atmospheric pressure, is 101.325 times 10 to the 3 pascals. That's a very large number, right? So it's not really a very convenient unit. Like it's kind of like this. Suppose I said, hey, I'm going to drive to New Jersey. How many inches is it? You could report that number, but you'd have this such a huge number that it just wouldn't be very convenient to use it. Even feet wouldn't be useful. Yards wouldn't be useful. So we do it in miles, right? Or kilometers. So same thing here. For atmospheric pressure, that's such a large number. What's the point? So here's what we generally do. We do kilo. So 10 to the 3 is kilo. So this would also be 101.325. Instead of 10 to the 3, just write kilo. So kilopascals. And then this is usually defined or referred to as one standard atmosphere. 1 ATM is atmospheric pressure. Now remember, atmospheric pressure changes, right? We do have storms that come in and out. A hurricane changes atmospheric pressure. Altitude is important. So it's defined in a particular way. It's got to be done at room temp, at sea level. It's got to be done at a certain temperature and all that stuff. But one standard atmosphere is 101.325 kilopascal. That's a lot of sig figs. So sometimes people just write it as 101.3 kilopascals. That's more convenient. Now we got something that's not that bad, right? Hey, how much pressure is one atmosphere? 101.3 kilopascals. So kilopascal is a very common unit that you'll see. There are other units as well. So we've got one atmosphere, 101.3 kilopascals. I'm going to just give you a couple of others. So the next one is torr. So an atmosphere is also 760 torr. And I'm not going to go through the whole history of that. There's a particular way in which you measure pressure using a barometer. And the barometer it's just useful to do it in terms of what we call torr. The older name for the torr is called a millimeter of mercury. So this is the same thing as 760 millimeters of mercury. MM for millimeter. That just, again, that unit just has to do with like the history of how you measure pressure. So these four are equal to each other. So the reason that we have to talk about this issue of so many different units, and there's other ones as well. So the reason we do it though is because different people use different units. So what do you call them? Meteorologists use different units. Physicists use different units, chemists use different units. When you do your gas law experiments, so I think there's 2 of them that you have to do coming up in a couple of weeks, those experiments will probably, you'll have units in torr or millimeters of mercury. But when we do these calculations, some of the times they're going to be in kilopascals. So, oh, there's one more. I'm just going to write it down. I don't think there's any that you have to do with this one. But if you're interested, this is called PSI, pounds per square inch. 14.7 PSI is pounds. So you'll see that. So bicycles or car tires are often calibrated in terms of PSI, pounds per square inch. So roughly speaking, 15 PSI is an atmosphere. And again, these are all the values that are atmospheric pressure. So on Tuesday, in our next meeting, what I will do is I'll look at a couple of calculations using these, and then we'll get into our gas laws and we'll start. So there's a lot of background here, but these are the numbers that you'll use for your calculations. Okay. All right. So reach out to me if you have any questions, and have a great end of the week and a good weekend. I hope everything is going well for you, and I hope you can have some productivity. I hope you have time and energy to be productive, and take care, everybody.
Thank you, Professor.
you.
Bye-bye.